Okay, so yesterday we were having a look at different support conditions on columns. So what we've got here is a table, and it introduces this idea of the effective length. So I'll try and explain the effective length again for a column, and after that we may show how that this value, the 0.7, is derived. So before we do that, remember everything is linear elastic. If we drew something like that, and then we say that's the load P, so this would be let's just call this the compression, and let's call this the tension. So and let's call that the deflection at the end, or you can denote that whatever you want. So if you took one of these and put it in tension, obviously it's got an axial stiffness, which you can calculate based on strain is change of length over original length. So let's just show that with a gradient. So as you increase the tension force, the thing extends. So if I increase the tension force, I know you can't see it, but if you extend the tension force here, this member here is going to get longer. If you apply it in compression, I know you can't see it, it should get shorter. So the gradient of whether it goes longer, so this would be the longer direction. So let's just I'll just say this is getting longer in tension, and then this side here is getting shorter in compression. So it's going to be the same gradient, whether it gets longer or shorter. And if it's linear elastic, which means that the stress strain curve, there's no stress strain curve, it's just linear elastic based around the Young's modulus, which for steel is about 210 times 10 to the 3 newtons per millimeter squared. So that gradient should be easily you should easily be able to calculate that gradient, whether it gets shorter or longer or shorter under compression. In tension, there's only one solution. In compression, there are two solutions. So one solution is just gets shorter and shorter and shorter as it crushes, or not crushes. It just gets shorter and shorter and shorter as the load is applied. And then there's another solution here where it can just break off there. So this one here is called the Euler, which is buckling. And buckling, as we said, occurs at pi squared EI over L squared. So in compression, there's two solutions. One of them is the Euler, pi squared EI over L effective squared. So that's one solution. And the other solution is this solution here, where it just goes off to infinity and it doesn't buckle. So only the Euler, I hope that you can see that, is the buckling solution. So this one, we'll call that it's known as the trivial solution. Exactly the same as I said, if you applied a load in tension instead of compression. So the compression has the trivial solution where it just compresses, but there's also another solution, which is the instability, or the Euler, or the buckling solution, and that occurs at pi squared EI over L squared. So if we wanted to trace the Euler solution, obviously, first of all, it's got to go up by the trivial solution until it meets this point here, where it can decide to continue on the trivial solution or go along the Euler solution, pi squared EI over L squared. And we can see here that if it goes along the buckling solution, which is the instability, that means that deflection shoot off to infinity. So as soon as you go along here, there's no increase in load, there's no gradient, that's a flat line. So as soon as you go along this one here, suddenly all deflections theoretically shoot off to infinity. So it's not really possible for a column to be able to carry more than the Euler load pi squared EI over L squared, because it would go unstable and everything would shoot off to infinity. So that's why in compression, this one is quite important to be able to at least have an appreciation of. So when you go off and design, the vernacular of the engineer is to use this term called the effective length. So I'll try and explain what the effective length is. So this one here, that one there relates to the fix case, which would be this one here. So remember I said well, the half sine wave length doesn't change because the deflections shoot off to infinity, so it just becomes a bit more compressed. So we would say, if I was able to remember, I said it can either go one way or the other. It just depends on any weakness in one direction in terms of the material as to whether it goes left or right. But hopefully you can, if that was perfectly rigid, which is not, because in real life there's always imperfections, so I'm trying to hold it with my fingers. So hopefully you can see that there is a half sine wavelength that goes along there, and it probably goes from here to here. So what I've got here is I've got another length which is approximately half of the original one, and hopefully you can see that when it's in the pin condition there, that half sine wavelength is almost the same as that half sine wavelength, which we can see there. Right, so I'll let that go. And so we could say the effective length of a fix case here, the effective length of the fix case here is half of that length. So half of this length would be about there, and we would say that the effective length of this can be related to pi squared EI over L squared for a length that's half of that length. So I hope that's clear, and this one should be relatively easy to derive in terms of where the half comes from. These two expressions are the same, by the way. So this is just saying that the buckling load is 4 times bigger over the entire length, and then that relates to an effective length of 0.5. So you can see the square root of 4 and going under to becoming the half. Right. So when we've got a different boundary condition, so take this one out here. So we'll put that to one side. So when we've got a different boundary condition, so in this case here, I've got fix, which is here, and I've got pin, which I've got there. So the engineers would want to know what the effective length is, and they want to know what the effective length is so that they can use pi squared EI over L effective squared. So we saw for this case here that the effective length is exactly half, so that would be the effective length of that one, which would be half of the total length. So in the case of a fixed pin, the question is, what is the effective length? So actually, if you have one of these, well, if they make one of these kits properly, so that there's no friction at the supports and the line of action is perfect, you could probably take a photograph of this and approximate and get a very good approximation of the effective length, which you can still do with this one here. So I'm just saying it can be observed visually. So putting it down here, once it reaches the Euler load, everything shoots off to infinity, as I've said. So theoretically, once you've reached the Euler load, so you may not see any deformations as I increase the load, and suddenly it buckles. So it's an instability where everything can suddenly shoot off to infinity as you gradually increase the load. So load is 0, I'm increasing it larger, 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 until I reach that point, and then a real column would just go like that. And if that track was longer, the same load, that would just buckle up to infinity, and all stresses and strains, everything would become infinity once you reach that point, because that line is shooting up to infinity. So with that, you could probably see the half sine wave length, or the buckled length. And if we just pretend that this represented the effective length of the column, which it doesn't exactly, but if we just pretend that it did, get this in place here. So these two, this one is the length, length L, okay, and I'll just hold it so you could say that the effective length is definitely going to be less than that length here. If it was pin, the effective length would be, if that was a pin, the effective length would be the actual length, or 1.0 times the actual length. So you can see here that the effective length, I would say it's definitely less than 1, definitely less than 0.9, definitely less than 0.8. So it's somewhere about 0.7, which we'll be proving later on. And hopefully you could see, I know I can't push them down at the same time, but hopefully you can see that this whole length could be the effective length of the buckled shape. So maybe I should have had this one a bit further along here. That might have been better. At least then these two would be starting from the same position. So hopefully you could see that the effective length of these, that the half sine wave length of these two are the same, or approximately the same. So that one's you can see that this one's not a perfect fix because of the tightness of getting the peg in the hole, which is great because we can talk about that later. But hopefully that demonstrates the concept of the effective length. So the engineer would say, what's the effective length of this column? And then we might say it's 0.7 of the entire column. And then you would do 0.7 times this length, which would then become the effective length. So if that was 1 meter, the effective length would be 0.7 of a meter. Let's just pretend that was 0.7 of a meter. And then you can work out the buckling load PCR using pi squared EI over 0.7 L or squared. So once you've got the effective length, you can just use that in the Euler expression. So it's a very quick way for an engineer to get a feel as to what the elastic critical buckling load is, or how it relates to the pin-pin condition. So I hope that's clear, and I hope I've explained what the trivial solution means. So we've got this example here. Where you are applying a load P. So I'll put the load there, P, to be calculated, and then we'll say that length is L has to be the entire length. Okay, L has to be the entire length. So let's set up the support, let's sort out the boundary conditions. So if you put P down there, there would also be a P down there because of the reaction. There would also be a bending moment, which we'll call MA. Doesn't matter whether it's that way or the other way. As you can see, when I showed it can either buckle to the left or to the buckle to the right. Let's set this out to have X. There needs to be a reaction at the bottom there, which I'll call RA. So obviously that's R and that's B. And then if RA acts in that direction, RB at the top must be acting in the opposite direction, just by equilibrium. So you could say that RB, which is that load there, is going to be equal to L times RB, the total length take moments, is going to be equal to MA, and that's going to be equal to RA multiplied by L again. So at a point X, which I could show there, let's just draw the buckle shape. So it's exactly the same as before. So we show the buckle shape there. So that would be my distance X. There would be the RA. The moment would be, let's just call this RA times L, because we've just calculated that. And then of course that's going to go P. Right at the top, so this would represent the distance X. So just take an arbitrary cut at the distance X. And then you've got your load coming down here, P. There would be a moment there, which I will call mx. So m as a function of x, so that would be the moment, m as a function of x. And then out here you would have your RA as well. So I'll just tidy that up, and I'll just put the hash lines to indicate that was the support, that was the fixed end supports. So I think we've got everything there, and then let's do the sum of the moment. Is going to be at the cut is going to be equal to 0. So that's by equilibrium, and then 0 is going to be equal to P times V, which is the displacement along that direction there, plus RA times X minus RA times L minus M as a function of X. So it's almost the same as what we did before. And then we do the substitution, minus RA L minus X, and then plus the curvature, so EI V double dash. So remember that the bending moment is the bending moment is proportional, or is equal to EI times the curvature. So from there we get EI V double dash plus PV is equal to RA times L minus X, and then we get the expression there. So we get the differential equation which you would have solved in the first year, and that's going to be equal to RA over EI L minus X. And then we'll, as before, we will let the alpha squared is equal to P over EI, and then you make that substitution. So after that there will be some maths which you can go through, and then right at the end of the process you will come up with tan alpha L is equal to alpha L. Okay, so so you go through the maths and you'll end up with tan alpha L is equal to alpha L. So you could solve that by trial and error. So I'll draw a graph there, and we'll call this tan alpha L, and we'll call this alpha L. So we've got tan alpha L equals alpha L. So first thing I'll do is to draw the alpha L, which we'll get down there. And then you would have the tan function, and then another tan, and then another tan function. So one way to, so that's not very well drawn. Okay. But one way to do it is just find the intersection of alpha L and tan alpha L, and then just read that off here. So you could do that by setting up a spreadsheet or something, and then you would get the alpha L is equal to 4.493 as the interception, and then you can pass that all back, and after you've done that, out will pop the 2.05, and then you'll get the 0.7. So if you, as I said yesterday, if you wanted to do that, you could go onto the Dropbox, and firstly you could look at what I call the previous instructor solution. So no, not that one. So you could look at this solution here where it's written out. There's also a guide or a revision for solving the differential equations, which I hope you can see. And then that's just what's been described here. That's the graph there, and then that's the intercept, the 4.93, and hopefully you can read that when you substitute it back, you're going to get the 2.05, which you can see down there, and then you can turn the 2.05 into the effective length. So that's 2.05, which you can then turn back to the effective length. So that's one solution, which some of you might be happy just to look at. If you wanted to, as I said, I've got a video where I talk about. You can see the graph that I've put up, so you can have a look at that, which is just me talking through the same solution. And then there's some other solutions. So Arthur's put up a solution. There's also a previous YouTube solution that I recorded a few years ago. So there should be enough there for you to work out what's happening. Okay, so that's just the evidence as to how to get the 2.05, and then from there you can relate that back to an effective length, which turns out to be 0.7. Right, so that's the first example. So effective length, I've talked about this before with the prop. So examination of the formula shows 1 over eta, where eta is some numerical value depending on the support condition. And then rearranging it, you can see the eta here and L, and that's where the effective length came up. So L effective is eta in the case of this one. Eta would be 0.7 times L. So it's the effective length. Note the last formula for the critical load is the same as the pi squared EI over L squared, where L in that case here is the total length. So we're just trying to relate everything back to a pin-pin condition, which we've got there by reducing the length of that one there. So this is illustrated here with the pin fix case. Effective length is widely used in design codes. So if you're working as an engineer, there'll be, the common question is, what is the effective length of that column, or what is the effective length of the beam in some cases? And it's not bad because it relates everything back to pin-pin. So it's a very, very quick way, and it's a very intuitive way to help understand boundary conditions. And you don't need to make any changes to the formula, as we've said before. So that just illustrates the effective length of this column here related back to the shorter strut here, the effective length is 0.7 of that. Now, there's another concept or another term, and this term is known as slenderness. So during our discussions of buckling, we noted that only slender columns buckle. So now we're in a position to quantify slenderness, which up to now we've used rather loosely. So let's first calculate the direct compressive stress in the member with a sectoral area A subjected to critical load. So I think I did a sketch down here, which we can see P over P against delta. So obviously if you know what P is, you know what the stress is. So you can convert the P into a stress, divide P divided by the cross-sectional area. So we know pi squared EI over L squared, or L effective squared, and we can divide that by A. So we've now got not a critical load pi squared EI over L squared, we've got a critical stress dividing the whole thing by A. So the ratio I over square root of A, so you should know this from the first semester, is also known as the radius of gyration, which is physically just how is the I, or how is the second moment of inertia, or how is the second moment of area distributed over the area. So you can see that here. So it describes how far from the cross-sectional neutral axis in an average sense is it related. In other words, for two cross-sections with equal areas, so this one and this one, they both have the same cross-sectional area. This one's got more material placed further away than this one here. So this one's got all of the material lumped near to the center, whereas this one here, it's further out. So the neutral axis will have the larger radius of gyration. So the radius of gyration of this one here would be larger than this one here. And this is illustrated in this figure here. So with that in mind, you can rewrite using this concept of the radius of gyration, which is defined as I over A, square rooted. So you could relate that back into here. So that expression and that one are the same, and then outplots this thing called slenderness. So slenderness, like effective length, is another term that engineers use, and it's given lambda. And lambda is the length. Okay, so lambda is the effective length divided by radius of gyration. So that means for every column in the world, you could go to, so you can go to any column in the world and work out its effective length and divide it by the radius of gyration, and then that column would have a slenderness, which is a numerical number that you can calculate. Thus describes how, so it describes how easily a member buckles. So it's a bit abstract, and it's widely applicable as it takes into account the radius of gyration rather than the section width or the height. So you're actually using R to define what the slenderness is. So now we've done our definitions. So this was quite nice actually, because if you remember, I had a support condition yesterday, and one of these here, and that just didn't want to rotate. So that's so you would, you know, if it wasn't completely free to rotate, that's an imperfect. So it's not a perfectly frictionless. This one is always friction. So the theoretical calculations have assumed there's no friction, but in real life there is friction. Or in this case here, you can see this one's not a perfectly rigid case. So because there is some flexibility, just because that peg doesn't exactly go into that hole there, as you can see. So there is some flexibility. there. So that would be your imperfect support conditions. So columns, real columns are not perfect. So all of our treatment up to now has been theoretical. And remember, I said that it's linear elastic, so I've not even touched upon the fact that materials have stress-strain curves. So, and you know, there's no such thing as a material that is linear elastic forever. So, let's just go back to steel again. So the stress-strain curve of steel, so the stress and the stress-strain curve of steel, and maybe it looks like that with go up and then fracture. So, and then that would be the Young's modulus E. So before we said it's linear elastic, or it's an elastic assumption, which means that it doesn't have any stress at which it might fail. Normally the stresses might be somewhere between maybe 250 up to maybe 700 for the stress at which you get the horizontal plateau going up to fracture. So I'll say just approximately between 200 and 700 newtons per millimeter squared in terms of the material failure. So that covers non-linear and non-elastic material properties. Sometimes you might come up with a damaged column, so, or the column in its initial unloaded position, it's not perfectly straight. So in what I do in my lab is that we've got laser scanners, and we actually scan sections before we put the load on, so that we know that how much the initial imperfection is. So that's called an initial imperfection, which means that the column may start its life already deformed even before we start to put some load on. So that would cover the initial lack of straightness. The other thing we talked about was maybe, you know, in the perfect world, the load of action would be going down the column, but in the real world, maybe you've got a connection coming in there, so the connection force P is already eccentric to going down through there, so that's already going to want to cause some bending in the member. So that would deal with the eccentric compressive load. That one we've covered before, and I'll talk about the non-slender. So imperfect support conditions, fixed supports of larger critical loads, such columns smaller, so design standards, which we've talked about. And then the fixed supports are difficult to realize in practice because it may have some resistance against rotation. So this one here, as I said, that's not a perfect fix, and neither is that a perfect pin at the end there. Lack of straightness we've just talked about, so it could start its life not along there in the unloaded case, but it could start there already. Okay, but so it could start in that shape already as being the unloaded case. So because of these imperfections, let's write at the we can start again with the moment curvature equation, which we've got there, but this time we've got the initial imperfection, which we can see there, V0 as a function of x. So that's the initial lack of straightness. So we're doing exactly what we did before for a pin pin. So we're doing mathematically, we're doing exactly what we did before for this case here, except we're assuming that it's going to start life off with an initial imperfection, and then we're going to continue to load and carry on. So it's not going to start life off 100% straight. So incidentally, the magnitudes of the initial imperfection, so obviously the biggest magnitude, which would cause the biggest damage, I think that's the wrong word, but the biggest imperfection would normally talking about L over 1,000 maybe. So if the length was 1 meter or 1,000 millimeters, you could reasonably expect that the strut or the column may have an initial imperfection of the order of about 1 millimeter. So it's just 1 millimeter off being perfectly straight. So that of course is exaggerated, but that's where we're starting. So lack of straightness is taken care of here. So rearrange your alpha squared as before, and you get that expression there, which is the non-homogeneous differential equation. And the general solution to that consists of the complementary solution and the particular solution. Okay, so there's two solutions which need to be added before. And as I said in the first lecture, we could assume they're going to be, we could even have assumed they're going to be sine functions right at the start. So the particular solution depends on V naught x, which is the initial imperfection, and we would just assume that it forms a half sine wave. So no one is saying that the initial imperfection has to be a half sine wave. It could be something like that in real life, or it could be maybe maybe something a bit more, maybe something like that. But we have to make an assumption, and not a bad assumption is to say that the initial imperfection is a half sine wave. So this is a good approximation of typically encountered initial deflections. So if you're really interested, just flick me an email and I can show you some of the laser scan results that we have to show the shape of the initial imperfection. So we're assuming it's got this magnitude A, which I just said, is maybe in the order of length over 1,000, but we'll just call it A for now on, where A is the deflection, is the initial deflection at mid height. And then the particular solution is then VP B sine pi x over L. Substituting that back in gives you that expression there. And then the general solution then becomes the deflection is equal, or the deflection at mid height. The deflection at mid height as a result of that load coming on with the column starting from not being perfectly straight is equal to the complementary plus the particular integral, and then you get that expression there. And then as before, we shove in the pin-pin boundary conditions at the ends. Deflection is 0, deflection is 0 at the two ends. From there, equation 25 is obvious, but this one requires more consideration. So the non-trivial solution, A is not 0, would require x pi L. However, the particular solution then becomes infinite. Because this is impossible, we assume A is equal to 0, and then we get this one here as the general solution. And then from there, you can rearrange that expression. So that would be your deflection at any position x. Just remember, x is going in that direction there, so that is the deflection at any position x going up from the column. So you've got this bit here, and then you can rearrange it down there, and then you would get V naught, which is the initial V naught, which is the initial imperfection, or what you defined as being the initial imperfection, and divide that by PCR, which would be pi squared EI over L squared over the load P that you've applied minus 1. And then the total deflection, i.e. the initial, due to buckling, can be written as V naught plus, V, which is the increase in deflection plus the initial one, and then you get V naught x 1 minus P over PCR. So just note that as a result of that arithmetic, these two bits have been reversed. Okay. So the proof of that Vx V naught x PCR over minus 1 gets there. So this guy there, that's the proof. Okay. So let's just have a think about what this expression means. So V total. So by total, it means how far it's come from when it was dead straight. Oops, so it's buckled that way that time. So how far has it come from that line, which would be V total. So V total is equal to V naught x, which would be the initial imperfection of magnitude with an amplitude, say, of L over 1,000 of the half sine wave function, and then you would be amplifying it sort of by 1 minus P, which is the load that you've put on, over PCR. So when your P reaches PCR, then you've got 1 minus 1, and we can see everything shoots off to infinity. So we should be able to see that on the graph on the next page. So we've got the mid-height additional deflection. So expression 30 is the same as expression 29, except that we're defined, so we've now defined that as, so that's under there, and then we've defined that as delta. Okay, so we define that as delta. So instead of having a function over the whole column, we're just interested in what's happening at the middle, and I think that's fair enough, and it simplifies things. So the deflection, or the delta at the center, is V L over 2. So that's the distance x, and that's the height. Okay. So when x is equal to L over 2, which is halfway up the column, that's a bit distracting, so substitute that in, and you're back to your A, which is the initial amplitude, PCR over P minus 1. So remember, A is something of the order of the total length divided by 1,000. That would be an appropriate magnitude for alpha, for A, in terms of the magnitude of the initial imperfection. So here's a graph, P over PCR, and as I said, when P reaches PCR, I said at the start, a column cannot carry a load more than its Euler load. So when that one is PCR, it's 1 minus 1, which is 0, which means that the deflection is infinity. So we can see that when it gets to infinity, when it gets to here, it shoots off to infinity, which is what you expect. And then down here on this axis here, we've shown delta as an delta over A. Okay, so we've got delta over A for this axis here. So this one's not bad. So you can see this expression going around here, going around there. So as the P approaches PCR, so there's a deflection approach infinity, and this means that there is no clearly defined buckling load, but the column will be destroyed. That's an interesting word. Well, yeah, destroyed before reaching the critical load for an initially straight column obtained from the P-Euler theorem. So going back to where we started, I was drawing, so going back to where we started off today, I said there was a trivial solution and there was an Euler solution. So if there wasn't any initial imperfection, then that would be the elastic solution. So that line is the same as that line. Of course, the scales now changed because I'm trying to relate it to that. And then that one would become the Euler. So before trivial solution, shoot up to infinity, assuming column is absolutely perfect and suffers from none of these issues. So perfect column would not have any of these issues here, but a real column would have an initial imperfection, and instead of going up like there and shooting up to infinity, we can see that this has now some roundness, but it's still it shoots up to infinity when it's equal to 1. So this is the plot of deflection at mid-height against P for the curve B. So now let's have a look at example 2. A pin-ended tube, 1.5 meters long, 25 millimeters outside diameter. So a pin-ended tube. I'll just choose to draw it like this. So a pin-ended tube, 1.5 meters long, so that's going to be 1.5 meters long. 25 millimeters outside diameter, so let's just draw the cross section there. So that's a tube, 25 millimeters outside, and so this one's not to scale, so 25 millimeters for the outside, and 2 millimeters wall thickness, so the inner diameter would be there, so that'd be 25 minus 4, which would give you 21 millimeters for the inner diameter. Has an initial curvature, so A is 5 over what is 5 millimeters. So if you wanted to, you could just say, I said that the typical imperfection is L over 1,000, so that L over 1,000, I guess that's going to be 1.5 millimeters. So my A is about three times more than the L over 1,000. So we're saying that the A in this case here is 5 millimeters. So at least that's in the same ballpark as to what I said. So it's probably like 2.5 L 2.5 over 1,000 times L. Okay, so it's telling you what the initial imperfection is, which is 5 millimeters. What is the maximum stress due to an axial load? So we stick an axial load there and there, and call that 3.5 kilonewtons. So 3.5 kilonewtons. So to solve that one, we're probably looking at these equations, and you'll be working out what the delta is at the mid height, which you can. So you got your PCR and then you got your P. So you can work out pi squared EI over L squared of that length, and then you can divide it by the P, which we've got there, because the P turns out to be 3.5. And then from there you can work out what the bending stress is, using sigma equals the moment, sigma equals my over I. So in order to do this one here, you have to work out what the I is of that. So if we go back here, so what I've done in terms of the solution is I've got a solution which hopefully would turn out there. So you can see my solution here. Yeah, okay. So you can see the solution that I've written out here. So all of that would be in this file here. Okay, so all of that would be under what I call previous instructor solution, which would be that one there. And then, as always, I've got a video that explains it. So hopefully that's the right video. So as I'll go through and talk about the solution, which you can see there. So those two things are there for you. And then you've got Arthur's solution. So in my solution, I choose to introduce what Lucas and Quincy may have talked about. So there's a distinction between thick wart theory and thin wart theory. So generally when engineers do calculations, we're normally doing thin wart theory, okay? Which is a bit confusing when you first see it, which is why I would like to introduce it to you here. And of course, when we get to the shear section of the course, most of it's talking about thin wart theory. So thin wart is using center lines. So if you remember that prop that I brought in the first lecture, you could it's so thin you could even trace the center line. Obviously there's an assumption involved in having the center line going around there, but as this becomes thinner and thinner, it becomes more and more accurate. So with the thick theory, I suppose pi r squared would give you the pi r squared would give you the area, and you could minus pi r squared there, and then you can get the area. With the thin wart theory, I would say you can get the area, you can approximate the area of the tube there by working out the circumference, which would be 2 pi r, and then I'll call that the mid. So that would be your r mid, or the midline, okay, which would be the dotted line. So you could work out the circumference of that line there, and you could multiply it by the thickness, and the thickness would be 2 millimeters, or that would be the thin. So the thick ward would be pi r squared minus pi r squared, and that would be the outer, or the outer there minus the inner. And hopefully you can see, or hopefully you can believe, that it would be this and this would be approximately the same as, and get closer and closer to each other as the thickness of the wall becomes thinner and thinner. Okay, so you can have that for area, and then you can have that for second moment of inertia as well. Okay, so if you watch the video, I'll be talking about thin wart theory, and that's just an introduction to thin wart theory, which we would have to use a lot more when we get to the shear portion of the course, and that's why I chose to talk about it in the video here. But of course, this solution is quite short anyway. So if you look at what Arthur's written out, he's got the solution down in about 10 lines or so. So you can see, and he's just used thick wart theory to work out the stress, which he calculated to be 63. Okay. So those are some things you can dig into when you look at the solution. So, something called the Southwell plot. So equation 30 can be rearranged into this expression there. So you can see how it's been arranged. revealing a linear relationship between P over delta and delta, and that's known as the Southwell plot. So using the Southwell method is not bad. So if I've got something in the lab, if I've got a column in the lab, I don't need to fail the column in order to estimate its elastic critical load. So I could put a load on the column like this here, and then I could increase the load, and then I could increase the load further, and I can just measure how much movement there's been as a result. And then from there, I would be able to estimate what the elastic critical buckling load is. So you can see that simple arrangement there, which then allows me to do a plot of deflection, center deflection measured in the lab against central deflection divided by the load that's been applied. So in this case here on the graph it shows as N, but it's the same as P. So yeah, it permits experimental determination of the buckling load. So I've used this before in my own testing in the lab to estimate what the buckling load is. So stick a load on P in the testing machine. Maybe we'll just call that P, just to increments of delta, and then you can plot that on the graph here. And then based on these plots that you've plotted on the graph here, what is the buckling load? So the buckling load is, you can see that is y equals mx plus c. So the buckling load would be the inverse of the gradient. So going along here, you can put your experimental plots here as you increase the load. You can work out the gradient between any 2 points, and you work out the gradient, and then y equals mx plus c, so y is equal to mx plus c, so we don't need to know what the c is, we just want to know what the gradient is, and then the inverse of the gradient would help you predict what PCR is, which in this case here is 13.85. So that's the Southwell plot. So next thing that we'll have a look at is the eccentric compressive load. So we've already talked about the load not coming on at dead center, which is almost impossible, but the load being applied off center. So again, it doesn't really matter which way it goes. Yeah, okay, well, it sort of does. So I'm putting a load off center here, and again, you can see the column is buckling. So, so far we've assumed the compressive load is applied at the centroid. Again, this is unlikely. This is unlikely to happen, so we're talking about eccentric compressive loads. So we've already dealt with the initial lack of straightness in terms of the maths. Here we're dealing with the eccentric compressive load. So we're now exploring when the load is applied off center. So moment curvature relationship again. So the bending moment is equal to EI times the curvature moment. So that would be the bending moment, and that would be E multiplied by Vx. So that's the difference between what we did before, right at the start, for the perfect column. Now we've got a distance E being applied. So as before, this can be simplified to here. This is an inhomogeneous equation, and it's got the following solutions for the pin-pin boundary condition, which we can see there. And then the mid-height is given by that distance there. So E, the eccentricity, 1 over cos pi 2 P over PCR. So when you use that, you're calculating that pi over 2 multiplied by p over PCR all square rooted, and then you're taking the cosine of that. So it's not cos pi over 2 multiplied by the square root of p over PCR. It's pi over 2 multiplied by p over PCR square rooted, and then you take the cosine of that. And when you do that, remember we're talking about radians. So when you do that in your calculator, remember you're doing radians. So as before, figure 10 shows how mid-height deflection changes with increasing load. So the figure has an initial shape caused by the initial lack of straightness. So when the eccentricity is 0, then we're back to what I drew right at the start of the lecture. When you're going up there and then shooting up to infinity. So obviously it doesn't show it, so you could say this is zoomed in to here because that trivial solution on a bigger plot would just be very, very near to the axis. Okay. So that's the trivial solution, and then that is pi squared EI over L squared when there's no eccentricity. But as we gradually put in the value of E for the eccentricity, you can see that the result change. You can see that the graph changes. So again, as axial load increases, so there's a deflection, and when P approaches the critical load for an initially straight column, the deflection shoots up to infinity. There's clearly no defined buckling load, but the column will be destroyed before reaching the critical load for an initially straight column by the Euler theorem. So this is all very nice talking theoretically about shooting up to infinity, but as we know in real life, the material or whatever material that you're using, that would have its own stress strain curve. So just this before. So I drew the stress strain curve of the steel. So all this, so Gary would have talked about dog bone columns being used in the laboratory to measure the Young's modulus and the stress strain curve, or Quincy would have been talking about it before. So although we're saying everything shoots up to infinity, we know it's not. We've got the material properties to contend with. So our treatment for these has been still the elastic assumption that the steel or whatever material it is doesn't have a yield point, because we'll just assume that stresses can go up to infinity, which they can't. So that deals with these. So the above formulas for eccentrically loaded columns were derived for the particular boundary conditions. Care must be taken when analysing other boundary conditions if it turns out that the cantilever column, equation 35, delta would denote the deflection at the tip. Okay. So if it's, so you can do the same treatment here, say for a cantilever column with your cantilever coming up there, and then you've got your axial load coming down with the cantilever, and it would be almost exactly the same as what's happening here with just the adjustments for the PCR, but that's what that's saying there. So you're doing an online exam, so which means it's effectively open book. So I'm not saying that there will be a derivation, but just get rid of that. So if there was something, you should already know how to solve a differential equation from year 1. So this should be nothing more than you already know, and just providing some notes for the general solution and the particular solution. If you've got any problems with that, just contact Arthur and he can have a chat with you. And that leads us to example 4. Okay, so example 4, we've got a pin-ended column, so pi squared EI over L squared, L is the effective length of 1. It's constructed from this. We've got the I's and we've got the A's. The column is subjected to a centrally applied load P and an eccentric one. So our pin-ended column, there is assumed to, I suppose in that case, it's assumed to have both a load there as well as a load there. So there's 2 loads to worry about, one going down the center as 1420 and the other one has been applied eccentrically. So physically that could be imagined as a bracket at the top of the column, whereas maybe a rail is going there and there could be a crane track going along here putting on a different load that's been applied eccentrically. So here it's giving you the second moment of inertias about both axes. So one of them is a red herring, so it's giving you both directions, but you don't need to know both. P loads at a bracket. Figure 11 shows the sketches, illustrating the problem. Bending occurs over 1, 1. So this axis here, so bending would be about that axis, not about that axis. This one is the strong axis, and this one is the weak axis. But in this case here, the bending occurs over the strong axis. Take the Young's modulus as 200 times 10 to the 3 newtons per millimeter squared, and then calculate the maximum compressive stress in the column under these 2 loads. So that's the example number 4, and at the next lecture I'll show where the solution is in the Dropbox, and you would also be able to, if you wanted to, these are some older solutions that I've done before. So once we've completed that, I think the last topic, or the last bit which we need to cover before we can wrap up buckling, would be consideration of the material, nonlinear material properties, and that's covered by this one here. And after that we will unify the theorems. After that we'll be unifying the theorems, and then finally we'll talk about the Perry-Robertson formula, which is the unification of all the imperfections plus the material imperfections that we've talked about. And the Perry-Robertson formula is how a designer in a design office would be designing a column. Okay? And that would combine both the material nonlinearity as well as the other ones that we've talked about today. So all combined. So all of this is combined into the Perry-Robertson formula, which is the last section of the coursework. I'm dealing with buckling, so we'll cover that all next time. So any questions, just post them on Piazza. And if you need some help with the maths or anything else, you've got Arthur's email address, and you can contact him and he can arrange some Zoom sessions with you, or you can contact me.